Hello. So we're going to draw a titration curve, looking at weak acids and bases titrated with strong bases and acids. So you might start with a solution of weak acid, and if you're starting with that, you're going to be titrating it with a strong base. There are four main points that you want to plot before you start drawing a curve. One of the points is just the initial pH. So if you're starting with a weak acid and you want to calculate the initial pH, you're going to use the Ka. Write a Ka expression and use the concentration and solve for pH. At the half equivalence point, the weak acid will equal the conjugate base, and pH equals pKa. This is a very easy one to calculate. You just got to position it right. At the equivalence point, all of your weak acid will have been converted into its conjugate base. So you're going to use Kb to figure out pH. And then past the equivalence point, you're going to use the concentration of hydroxide that had been added after the equivalence point. So that's if you're starting with a weak acid. If you're starting with a weak base, everything just kind of flips. Weak base, you're titrating with a strong acid. If you want the initial pH, you're going to need, since you're using a weak base, or you're starting with a weak base, you're going to use Kb. Kb is going to let you find the concentration of hydroxide, and then you can calculate pOH and then pH. At the half equivalence point, same, weak base equals its conjugate acid. pH equals pKa. Notice these are the same. We're dealing with pKa anyway. And at the equivalence point, all of your weak base will have been converted to its conjugate acid. So you're going to use Ka to find the pH. Past the equivalence point, you will be adding more and more strong acid. So you figure out how many moles of hydronium you've added and figure out the concentration. Don't forget that it's being diluted. So you're not just looking at the concentration of acid, you want to know in that new volume. So let's... Okay, so got this problem. 50 milliliters of 0.4 molar hydroiodic acid are added to 100 milliliters of 0.15 molar ammonia. We have a Kb value, we have an initial concentration, we have a concentration of our strong acid. Draw a titration curve that shows the pH changes. All right, so we're dealing with this situation. We're starting with a weak base, adding a strong acid. So this is what we're going to do. Well, first, we need to find the initial pH. We're going to use Kb to find that. The next point that you want to find is the pH at the equivalence point. Because once you know where the equivalence point is, it's very easy to position the half equivalence point. So we're going to do this one first and then this one. All right, so the initial pH, we're going to use Kb. And if you could make an ice chart, we're writing in the expression. If you're doing an ice table, 0.150 minus x, but that x, we're going to ignore it. It should be fairly small. So if you solve this, you end up getting a pOH value of 2.78 and a pH of 11.22. Okay, now we need to figure out where the equivalence point is, first for one thing, and then what is its pH. So for the equivalence point, we need to remember this is the reaction that's taking place. There's ammonia and hydronium reacting to form ammonium. So when we have equimolar ammonia and hydronium, that's where the equivalence point is, right? When you have a stoichiometric amount, the exact number of moles of each of these things. So what you need to do is figure out how many moles of this weak base you started with, and you need to add the same number of moles of strong acid, of hydronium. So the volume of our weak base was 100 milliliters, so 0.1 liters. And we multiply by the concentration, and we get 1.5 times 10 to the negative second moles of NH3. Okay, that's how much hydronium we need to add if we're going to neutralize it. We're going to turn all of the base into hydronium. So we take that number of moles and we use the concentration to figure out a volume. And the equivalence point is going to occur at 0.0375 liters So 37.5 milliliters for the volume units on this graph. Yeah, that's one thing. It gives us somewhere there. But we now need the pH. So well, at the equivalence point, all of the ammonia has been protonated. Right? It has had a proton attached to it. So we have, not 1.5 moles. We have 1.5 times 10 to the negative second moles of ammonium. Remember we calculated this? That's how much ammonia there is? Well, that's how much ammonium there's going to be. So we need concentration, not moles. So you take the moles of ammonium and you divide by the total volume. So you started with 0.1 liters of ammonia, you added 37.5 milliliters, 0.0375 liters, say it away, of hydroiodic acid. So you need that total volume. And you get a concentration of 0.109 molar ammonia. All right, so now what we have is a weak acid. If you go back to the first one. Right, at the equivalence point, if you're taking a weak base and you're adding a strong acid, at the equivalence point you have the conjugate acid. So you use Ka for the to find the pH. So we've got a Ka. Ka is Kw over Kb. They gave us the Kb for ammonia. Again, right, you have this minus x, we ignore x, we get x equals this. This is the H plus concentration, so the pH is 5.11. All right, so our equivalence point, we know it's x-axis value. Now we know its y-axis value. And I'm just going to approximate. What was it? 5.1. The shape of the graph at the equivalence point is going to be very important, but let's first get everything else drawn in. All right, so this, by the way, this 1.0 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5th, that's your Ka, that's 5.56 times 10 to the negative 10th. So half equivalence is when half of the amount of hydronium necessary to reach the equivalence point has been added. 37.5 milliliters was how much we needed to reach the equivalence point. We divide that by 2, we get 18.75 milliliters is where your half equivalence point is going to take place. And at that point, pH equals pKa. The reason for this, so make sure that you do, is that Ka the reason for this is that at your half equivalence point, the concentration of NH3 and NH4 plus are equal. And if they're equal, then they're no longer a factor, and Ka equals H plus, or pKa equals pH. So that's why. And we get a pH of 9.26. So we got 18.75 milliliters and 9.26. Oh, I'm just estimating here. Somewhere here. All right, so we have, it's close. So we have 3 points. We'll get one more, and then we'll make sure that the shape of the graph is a good one. What we're going to do is we're going to calculate the pH at the very end, when all 50 milliliters of the HCl have been added. And for final pH, calculate the number of moles of H plus added past the equivalence point. So, and the final volume of HI, like I just said, is 50 milliliters. So 50 milliliters we added. 37.5 milliliters is how much we added to reach the equivalence point. So we've got 12.5 molar milliliters of excess HI. 12.5 milliliters added that did not react, so the H plus is still there. So we make that liters, 0.0125, multiply, and we get 0.00500 moles of HI, or moles of H plus, because it's a strong acid, excess. Well, we need concentration, so we divide this by the total volume. The initial volume of ammonia was 0.1 liters, and the total volume of strong acid, of HI added, was 0.05 liters, and we get a concentration 0.033, and we get a pH of 1.48. So we go back. All right, we got these 4 points, and looking at it, I don't know if my graph is off a little bit, but I could draw a straight line and and pretend that that's right, but that's not the way these work. At the half equivalence point, that's where you have a weak acid and its conjugate base, and so that solution is going to resist changes in pH. That solution can accept protons, that solution can donate protons. So you're going to have a very minimal slope right around the half equivalence point. Conversely, when we get to the equivalence point, beyond this point, there is no weak base left to accept protons. So the pH will change very rapidly, very close to the equivalence point. So there should be a very steep slope here and a very gradual slope here. Kind of make it like that, and then I kind of missed, but that's okay. Missed that one too, but this is pretty close. So you get the idea. You should have this. It should be sloping downward, obviously, but it should be very, very slight in that region. I might have made it a bit too flat, but that's pretty reasonable. And I kind of missed here. I should have